This is section 3.5, rational functions and their graphs. First of all, what is a rational function? It is a fraction-like thing. We have a polynomial in the top and a polynomial in the bottom. Okay, that's basically all this is. The bottom is never allowed to equal 0 because we are never allowed to divide by 0. And so what we have to be aware of a lot of the time is the domain of the particular function we are dealing with. Now, where we might run into problems is in the denominator. The denominator cannot equal 0, so we have to be aware of where that happens every time. So our first few problems are just to find the domain. And this is going to end up being a small part of a much bigger problem. When you're asked to find the domain, all you worry about is the denominator. We set the denominator equal to 0 and solve that equation. Whatever answers we get from this equation, those are the numbers that are not part of the domain here. And you may be wondering, well, what do we do with the numerator? When you're finding the domain, you ignore the numerator. Is the numerator important in the big scheme? Absolutely. We'll be paying attention to it a whole lot as we go through and we end up graphing these things. But for domain, it doesn't really matter what's there. Now, there are two ways you can work this. It is a difference of squares, so it's easily factored. Or you may recognize that you can get x squared by itself very easily. And then you can use the square root property to get your answers as x equal plus or minus 8. So these are the two numbers that must be removed from the domain. Okay. Now they may ask you just to list the numbers that are not part of the domain, and you would just list -8, 8. They may ask you to give the domain in interval notation, in which case it would be from -infinity all the way up to -8, parentheses because we don't include -8, union, start at -8 again, but with parentheses, all the way up to 8, but not including 8, and then from 8, not including 8, up to infinity. So if they ask for your domain in interval notation, this is what you would do. They may ask you to write your answer in set builder notation. And this, so in that case, what the domain would look like, it is the set of all x such that x does not equal -8 or 8. Personally, I prefer this notation. This is set builder notation. Okay? So that's all we were asked to do for this one, find the domain. Do the same thing here. Take your denominator and set it equal to 0. And then, well, this is also set up for square root properties. I'm going to subtract 49 from both sides. I get x squared equal to -49. Take the square root of both sides, put a plus or minus here, and you get that x equals plus or minus 7i. Since we got a complex answer here, this is not going to be an issue as part of our domain because we're really only looking for real numbers that must be excluded. So in this case, this thing is never undefined. Which means that it's never 0 in the denominator, so we don't have any issues with the domain. The domain in interval notation would be -infinity to +infinity. Okay. Another notation you may have seen before, it is not in your book. Since there are no issues here, we would say all real numbers, and the symbol for all real numbers look like that. Okay. Now, if you were doing paper tests and you were in my classroom and you told me the domain was all real numbers and I didn't specifically say interval notation, I'd give you credit for it because you understand it. But, you know, just in case you saw that in high school. Okay. Another little bit of things that we have to talk about is arrow notation. Now, in general, our graphs are going to be split in some way, okay? And this says, this symbol right here, x arrow a plus. This is read as x approaches a from the right or from the positive side. You can think of it that way. So what happens when our x values get close to a when we're coming in from the right? X approaches a with a negative is read a as x approaches a from the left. So as our x values get close to a when we're coming close to it from the left-hand side, what happens? X approaches positive infinity. So as our x values go way, way, way out, what's our graph generally doing? And you're going to see examples with this, so don't worry about it just yet if you're not completely getting it. And this is read as x approaches negative infinity. So as our x values get smaller and smaller and smaller, what happens to our graph? Okay, now we're going to talk about the most basic rational function, which is f of x equals 1 over x. It's called the reciprocal function because it just takes the reciprocal of whatever value you plug in for x. Okay, and this is our basic graph, and I apologize for my inadequate computer drawing abilities, but it's basically there. You'll notice that our graph gets really, really close to the y-axis here, but it actually never touches it or crosses it. The same thing is happening here with our x values, our x-axis. Okay, these have special names. We'll talk about them in just a second. But if you're using arrow notation here, what you can see, this says as x approaches 0 from the negative side, or as x approaches 0 from the left. So as our x values get closer and closer and closer to 0 from the left-hand side, our graph goes way down. Our graph goes to negative infinity. So as our x values get close to 0 coming in from the left, our graph is shooting down to negative infinity. As x approaches 0 from the right, so we're coming in on this side, imagine yourself traveling along your graph coming in close to 0. What is your graph doing? Well, we're shooting straight up. We're going to positive infinity. Okay? Now, as x approaches infinity, so as our x values get larger and larger and larger and larger and larger, what do we get close to? We're getting close to 0. We don't actually touch it, but we get really close. And then the same thing's happening as our x values go to negative infinity. So start on your graph, your x values get smaller and smaller and smaller. Your graph is getting closer and closer to 0, or the x-axis. Okay? Now, what are these two things called? The vertical and horizontal lines that the graph never touches or crosses are called asymptotes. Okay? The word is derived from the Greek word that, just because I wanted to look it up and type it in, and there's no other good reason for that, I'll be perfectly honest. And it means not meeting. So our graphs, we have some basically like controlling parts of our graph. They're going to require that our graph get really, really close to it, but never touch it. Okay? Now, in order to get a general rational function graphed, we have to locate these asymptotes. And so, we'll start off with the vertical asymptote. The line x equal a, x equals means it's a vertical line, is a vertical asymptote of the graph of f if f increases or decreases without bound as x approaches a from either side. Okay, so this says as we're getting close to this number, whatever it is, either and from the right and from the left, our graph either goes to positive or negative infinity. Let's look at this graph right here. Our y-axis is our vertical asymptote. As we come into it from the left, our graph shoots down. As we come in from the right, our graph shoots up. Basically, by a vertical asymptote, they'll either both go up, they'll both go down, or you'll have some sort of split, but they will always be going to an infinity. One direction or another, always to infinity. Okay? So how do we locate these? First thing you have to do is you have to put your function in lowest terms. Okay? And then you look at the denominator, wherever the denominator is 0 after that. After you reduce it, then you're going to have a vertical asymptote there. All right. So this right here, we're going to locate the vertical asymptote for. It is the same thing as we found right here, okay, when we found the domain. In the domain, we did not put it in lowest terms first. Let's look right here. We need to see if this goes in lowest terms. Well, that means factoring everything. X plus 8 does not factor. I'm going to put it in parentheses because if it cancels out, it has to cancel out as a unit. Now this is over. I'm going to factor this. X squared minus 64 is a difference of squares, so it factors as x plus 8, x minus 8. And then this does reduce. And you end up with 1 over x minus 8. Okay. So I have it in lowest terms now. Now what do? Now I take this denominator and set it equal to 0. Okay. And solve this, you get x equal to 8. So that means we are going to have a vertical asymptote at x equal to 8. Okay. One thing here, our domain and our vertical asymptotes are related, but they are not the same. Right here, we had to eliminate -8 and +8. Okay. Our vertical asymptote is always going to be listed here. It's, our vertical asymptote is always not part of the domain. But it is possible to have things that are not part of the domain, like this -8, that are not vertical asymptotes. Okay? And just a note here. You will have a hole in your graph, and we're going to talk a lot more about this. At any value that was not part of the domain, but is not a vertical asymptote. And by the way, I'm just going to write VA for vertical asymptote most of the time because I'm lazy. Okay, so I had x equal to 8, which was not part of our domain, but -8 ended up not being a vertical asymptote, so I'm going to have a hole there, and we will talk about how to deal with all of that. Okay, so let's do this one. We want to find the vertical asymptote if it has one. And it's possible that it doesn't. It's also possible that it has more than one. Okay, so I look at this. It's already factored for me. I see if there's anything that I can cancel. And x plus 3 would have to cancel out as a unit if it canceled out at all. And it doesn't. So now I look at it. It's already in lowest terms. So I set the denominator equal to 0. Okay, now it's factored equal to 0, so you split it up, x equals 0, or x minus 3 equals 0. So x equals 0 is one vertical asymptote, and then x equal to 3 is another. So this particular problem had 2. Okay. So what I want to do is I want to reduce this if I can, so I need to try to factor in the numerator. Two numbers that multiply to a -21 and add to a 4 would be 7 and -3. So I have x minus 3, x plus 7, over x plus 7, which did not factor. And then these cancel out. And I have just x minus 3, which means I no longer have a rational here. I have a linear function. So that means there's no vertical asymptote. But it does have a hole. Hole at, what makes this a 0? -7, right? So -7 would not be part of our domain. Okay? So on these a lot, you're asked to identify a vertical asymptote and whether or not you have a hole. So that means you find your domain first, then you reduce it. After it's reduced, you can find your vertical asymptote. And anything that was not part of the domain that ended up not being a vertical asymptote is going to be a hole. Now, you're going to end up needing to graph a hole, which means we just draw a little circle there. Okay, but our graph still looks like it goes through that point. So if I have a hole at -7, how do I find the y value for it? I take this value and I plug it in here in the reduced form. So I take -7 minus 3, and I get -10. And this would be my y value of the hole. So I have a hole at the point -7, -10. So at -7, -10, I would go draw a little circle, and I would know my graph appears to go through it, so it's nice to have, but it doesn't actually exist at that point. Now I'm going to back up to here where I said we had a hole. We're going to have a hole at -8. Now we take -8 and we plug it into our reduced form, and we have 1 over -8 minus 8, so this would be -1/16. So our hole, we would graph it at -8, -1/16.